Hello! Hey guys, we're here. Now what we're doing now is for the stopping activity. Remember back in chapter 2, we took our reflex time, figured out at our reflex time how fast or how far we would go at 3 different speeds before we could stop, before we could hit the brakes. We tried at 25 miles per hour, 11.2 meters per second, which is the fastest you can go in a residential zone. We tried at 65 miles an hour, which is 29.1 meters per second, which is the fastest you can go on the freeway legally. And then we tried at your car's max speed, which is whatever your car's max speed is. Now, these were all how far you would go before you could even respond. What we're doing now is we're adding in how far you would go once you've responded, you floored the brake, how far are you going to go before you come to a complete stop? So let's start out a little bit about how are we going to figure out our acceleration. So the force of friction is equal to mu times the normal force. And that equals ma. Now the normal force on flat ground is equal to the force of gravity, right? And on flat ground, gravity is equal to your mass times 9.8 meters per second squared. And that equals mass times acceleration. F equals ma. So let's figure out what that is. Maybe I'm going to switch to another green marker. This is getting a little light. So we assume that your car has anti-lock brakes because every car sold in America for the last 20 years has had anti-lock brakes. Anti-lock brakes keep your tires from locking. You do not skid. You do not slide. So we're using our coefficient of static friction for rubber on dry concrete because we are in Southern California where the concrete is dry. They give us a value of 1.0 for a coefficient of friction. There are no units, by the way, for coefficient of friction. Times the mass. My car is 1,567 kilograms. And then, of course, acceleration is 9.8 meters per second squared. And that equals 1,567 kg times acceleration. Now, one thing you'll notice, I got the mass on both sides. I could divide both sides by 1,567 kilograms. I don't know if you need me. Well, what the heck, I'll do it anyway. So divide by both sides by 1,567 kg over 1,567 kg, and they cancel. And 1 times 9.8 is 9.8 meters per second squared is equal to acceleration. Now, I will tell you, nobody ever talks about cars with braking because generally most cars brake at pretty much exactly the same speed. What really has a big impact is not the brakes. Every brake system is strong enough to lock your tires, but it never will let you do that because everybody has anti-lock brakes. The big factor is the tires. We're just going to assume that you have whatever the tires are that they're talking about in the textbook. Chances are you may have a much better tire surface, a tire that grips a lot better than that. But for the sake of this, we're all going to say we have the same tires, so we're going from there. So acceleration is 9.8. So what do we know? Well, let's see. We know that our initial velocity, now, by the way, I'm just going to do the one with my car's maximum velocity. My car is an electric car. It's an economy electric car. So we know that my initial velocity that I'm going to be starting at is 42 meters per second. We know acceleration will be, now by the way, we're slowing down, so this is not negative 9.8 meters per second squared is going to be, oh, hold on. Acceleration is going to be negative 9.8 meters per second squared. Now, do we know our final velocity? A lot of people say no, but think about it. What are we trying to do? We're trying to stop. If I'm coming to a stop, my final velocity should should be 0, right? I am coming to a stop. So I know 3 things, and what I'm trying to find out is how far am I going to go before I stop? What is going to be my final displacement? Now, if we go back to chapter 2, we can find some formulas. Which formula are we going to use? So we got our 3 formulas to work with here, okay? The first one, delta x is 1/2 vi plus vf delta t. Is that our formula? Well, it doesn't have acceleration, and it does have time. Well, we don't know how long it took us, how much time passed before we stopped. So, not really the right formula. Now, this one does have stuff we need. Final velocity, initial velocity, acceleration, but then again, there's that delta t. This would tell us how much time it takes to stop, but not how far you go. Now, you could use this if you want. You could say, okay, I'm going to find out how long it's going to take me to stop. Then I'm going to plug it up here, take that time, plug it in the time here, and then figure out. You could do that, but that's a 2-step. There's got to be an easier way. Here's one. Well, this would tell us how far, but again, I would need to know how long it took. If I did this one, I could plug it in here, and that would tell me, but then it's a 2-step again. But what about this one? It's got delta x, it's got acceleration, and my velocities. This is everything we need to know, and it's all in 1 step. So shall we use that? Let's see, where do I have the most room on the board? We'll just do it over here. All right. So, VF squared is 0 squared is equal to VI. We're starting out at 42 meters per second. And that's going to be squared. Plus 2 times negative 9.8 meters per second squared times delta x. Okay, I think I got that down here. So 176. What? All right, there we go. So 0 squared is 0 is equal to 1,764. It is though equal to 1,764. Now, I even squared the units, so that becomes meters squared. Second becomes second squared. Okay, plus a negative 2 times 9.8 is minus 19.6 meters per second squared times delta x. All right, going further here, I can subtract 1,764 meters squared per second squared minus 1,764 meters squared per second squared, and I end up with negative 1,764 meters squared per second squared is equal to negative 19.6 meters per second squared times delta x. And let's just take all this. Let's take all this and move it up here, okay? Because I'm getting tired of crouching down, okay? So let's just take a look at what it looks like. So we have negative 17.64 meters squared per second squared is equal to negative 19.6 meters per second squared delta x. That's what that was. I just moved it up here because I'm tired of crouching down, frankly. So, divide both sides by negative 19.6 meters per second squared. Negative 19.6 meters per second squared. Now, negatives are going to cancel. Well, this whole thing is going to cancel. And let's see. If I divide these together, I actually, ironically enough, get 90, pretty much exactly. Somehow. So So I end up with 90. Now, second squared, cancel second squared, meters, cancel meters per second, and I get 90 meters. Really? Is that what I get? Hold on. Well, can't do anything about it. My calculator is my phone. I think that's what I get. We're going with it. I think it's 90. Could be wrong. Never know. So, 90 meters is equal to delta x. Now that's how far I'm going to go from when I hit the brake pedal to when my car comes to a stop. Your number is probably going to be a lot higher because, quite frankly, your car probably goes faster than my car. But this is a big distance. I mean, if you add in the 11 meters or so it takes me to even respond, for my reflexes to even realize, oh my God, I got to stop, and I hit the brakes, you add that onto this, you've got an entire football field that I've covered. And your car's probably faster than mine. So, long story short, don't go as fast as you can through a residential zone. It could end up very badly. Now, by the way, you're going to do this not just for your maximum speed, you're going to also do it for 25 miles per hour, which is equal to 11 meters per second. You're also going to do it for 65 miles per hour, which is going to equal 29.1 meters per second. So you need to do these two values, first this, and then your maximum speed, okay? Also, please, maybe record your maximum speed. I think there might be a question at the end of this, okay? Have a nice weekend.